Hello everyone, I'm Norman Wahlberger. Today we're carrying on with our Sociology and Pure Mathematics series. We're moving into the 19th century, we're looking at the history of geometry, and this is a really critical epoch in terms of the sociology of pure mathematics, because pure mathematics as a really sort of identifiably separate discipline from applied mathematics raises its head, I think, for the first time somewhere in the 19th century. Now, tracking exactly when this occurred is very subtle and delicate business. And there's, of course, been aspects of pure mathematics throughout the history, but I think it's pretty safe to say that for the majority of the history of mathematics, the focus has been very much in the applied direction, even though often applied mathematicians were interested in the theoretical aspects of their investigations. But the idea that there was a completely separate kind of discipline from the real world, the real everyday world of science and, observable phenomena, that was this world of pure mathematics, and that it was not necessarily directly in step with science or with observational reality. That, I think, first emerged in the 19th century, and I think we can trace some of its origins to this very big broadening of understanding with respect to geometry that occurred during this time. So I want to tell you about this because it's essential for a sociological person interested in this story to appreciate this huge flowering of geometry that took place in the 19th century. It was a golden time for the subject. And one of the really interesting, if somewhat sort of disappointing aspects of the subject is that in the 20th century, this took a nosedive, and the importance of geometry much diminished, even though it was still around, but not in the glory that it was in the 19th century. So trying to understand why that happened, what was responsible, what were the forces at play, what were the reasons. This is something that there'll probably be a wide variety of opinions in the mathematical community. And I think it's safe to say that the entire question really needs somebody with some sociological training, some historical training perhaps, to investigate this. It's not purely a mathematical issue. So to prepare you for that, today we're going to talk about a number of different aspects of 19th century mathematics, concentrating on geometry. But of course, I have to keep in mind that you are maybe math phobic. Okay, you're a sociologist. You haven't had extensive training in mathematics. You may never have even taken a first-year course at the university level in mathematics. You may have dropped out of mathematics in high school. So I have to attempt to lay out what's going on here in a very general bird's eye view. Okay, so I'm going to simplify things and I'm going to leave out lots of things. But I'm hoping that my explanation will still be meaningful to you. So let's jump in. Well, let's start. There are lots of different geometries involved. And let's start with inversive or Mobius geometry, okay, named after a German mathematician, Mobius. And this is a geometry where circles play the dominant role. So we're talking about the plane, and we're thinking about circles. We're especially interested in circles. And there's a particular kind of operation that you can do with a circle called inversion. So I have to explain what that is. So here's a circle, okay? Its name is C. I'm going to explain to you inversion, say denoted by I sub C, in circle C. What this is a way of starting with a point somewhere in the plane and associating to it another point, say B, in the plane. So that this is a sort of a reverse operation. If you apply this inversion to A, you get B. If you apply the inversion to B, you get A. And this inversion has a lot of really beautiful properties, and it's very important in lots of things. So how do I define this? Well, there's a number of ways. I'm going to choose this way. That here's the point A. Suppose that it's outside the circle, okay? And here is the Apollonius dual of that point, or sometimes called the polar. And I remind you that that's one way to think about it, is to look at the tangents from the point A to the circle. Okay, the tangents meet the circle at these 2 points. That determines this dual or polar line. Now, The point B that we're interested in is on this polar line. And it's the meet of this polar line with the line from the center of the circle to A. All right? So that's how you get B from A. Now that also works the other way around. If you started with B and you took the polar line of B with respect to the circle, which is a projective idea, which makes sense, then you would intersect with that line again and you would get A. So this is a really important notion which has remarkable properties. The most remarkable, perhaps immediately, is the property that it takes circles to circles. Okay, I have to say that a little bit more carefully. It actually takes circles/lines to circles/lines. So let me try to illustrate that. So the inversion of this point A is this point B. Suppose that I take a little circle over here that happens to pass through A. And I look at the inversion of a number of points on A. So I populate this with a bunch of points, and I calculate the inverse of each one of these points. And I'm going to get, like for this one here, I have to find the polar, then I have to join the polar with the line from the center to there, so I'm going to get some other point. It turns out that what I'm going to get is another circle, okay? And the circle's a smaller circle, which was sort of like this, okay? So every point on this circle, its inverse will be a point on this circle. And conversely, the image of that circle will be this. Now, there's another sort of case that needs to be looked at. If you have a line, so for example, if I drew a line through our point A, okay, some line like this, and I looked at a lot of points on the line and calculated their inverses in this sense with respect to C, then what I'm going to get is another circle. And it's a circle that, it goes through this point B, but it also goes through the origin O, okay? And so it will probably be something like this. So it's not entirely true that the image of circles are always circles, because the image of this circle passing through the center is not, in fact, another circle, but rather a line. So for the purposes of this Mobius geometry, you have to think of lines as sort of being really big circles. Okay? You could think of them maybe as circles whose center is really far away, maybe at infinity in some sense. And in fact, you actually do need to think about infinity, because if you ask, well, what's the inverse of the center itself? There's no point in the plane which plays the role of the inverse of the center. And that means that you have to actually augment this plane with a distant point, a new point, which we call the point at infinity. So it's a very rich geometry, and okay, it's an example of a geometry where the main objects are not points and lines as they usually are, but rather these circles. So geometry of circles, which was discovered in the first half of the 19th century. Now it turns out this inversive geometry of Mobius is somehow intimately connected also with the sphere. And on a sphere, here's an example of a sphere in 3 dimensions, there's also a notion of circle. Because if you intersect this sphere with a plane, then you're going to get a circle on the surface of the sphere. In the case when the plane is passing through the center of the sphere, you're going to get a great circle, the biggest kind of circle, which is like an equator. Okay, like the equator is an example of a great circle. So are these lines of longitude. Now, there's a relationship between the sphere and a plane, which is a kind of mapping, a way of mapping the sphere or most of the sphere onto a plane called stereographic projection. And what that is, it's represented by this thing here. So here's the sphere. Okay, and imagine an equatorial plane. So imagine a plane which is passing through the equator. Okay, and So we're going to define a map from points on the surface of the sphere to points in this equatorial plane, possibly outside, possibly inside the sphere. So how do we do that? Well, we start with the North Pole. There it is right up there. Okay, North Pole, we designate that as a special point. Now if we have any point P on the sphere, we join the North Pole to this point P with a straight line. Okay, so imagine a straight line passing through the North Pole and the point P. That comes out, perhaps, of the sphere and will meet this equatorial plane in a particular point. Say in this case, R. Okay, so there's that line, and it sort of goes through the sphere, comes out, and meets this equatorial plane at this point R. That then gives us a map from points on the sphere to points in the plane. If P is in the northern hemisphere, like this one, then you're going to get a point outside the sphere. However, if P is down here somewhere in the southern hemisphere, then the line through the North Pole and this point will meet this equatorial plane in a point inside the sphere. There's only really one point that doesn't have a good image, which is the North Pole itself. Okay? And that sort of course, if you actually looked at the image of a point as it moves towards the North Pole, the corresponding image in the equatorial plane will go further and further away. And so it's usual to sort of think of the North Pole as being represented by a point at infinity in this equatorial plane. So that fits really nicely with what we were just talking about with this inversive plane and Mobius. And in fact, there's an intimate connection between the stereographic projection and the inversive geometry of Mobius. Okay? So you can see that by analyzing what happens when you look at not just a point, but actually a circle on the sphere. Okay? So suppose you take some circle. So you slice the sphere with the plane, and then you're getting a circle. And then you look at the image of that circle under this stereographic projection. So for every point, or for lots of points on the circle, you compute their images on the equatorial plane, and you plot them, and lo and behold, you find that you're getting a perfect circle. The image of a circle on the surface here is a circle in the plane. Unless the circle that you've chosen happens to go through the North Pole. In that case, the image is a line. So stereographic projection interchanges circles on a sphere with circles on an equatorial plane, where we sort of enlarge our view of circles in the plane to include these lines. And then it turns out that inversion in a fixed circle in the plane has a really nice correspondence in the terms of the geometry of this sphere. Okay? So for example, suppose you have some circle in the plane, and you're interested in inversion in this circle. And let's say that under stereographic projection, this circle in the plane corresponds to a little green circle on the sphere. So this little green circle on the sphere, okay, if you imagine tangents to the sphere, if you draw all the tangents to all the points on this little circle that you've got, okay, they will all meet at a point outside here somewhere. Okay, so another way of thinking about that is if you kind of imagine like an ice cream cone with an apex outside and enveloping the sphere, tangent to the sphere, then that associates to the original circle a point. And it's that point that's out here somewhere that is responsible for the inversion at the level of the sphere. How? So we take this point, I haven't drawn it, it would be out here somewhere in this example. And what we do is we use that point to interchange a point on the sphere with the other point on the sphere, which is obtained by taking the line from this distinguished point, drawing it through the point on the sphere and out the other side. Okay, so once we have a fixed point outside the sphere, then by drawing lines through that fixed point, that gives us a way of interchanging points on the sphere. And because the circle that we started with, the points on it are obtained by looking at tangents, those points are going to be fixed under this sort of reflection. And so the net effect is that this sort of reflection in this external point ends up being the spherical version of inversion in the corresponding circle in the plane. Okay, that's a whole mouthful, a whole theory there, which I've just sort of given you in a few minutes. I don't want you necessarily to understand all of it. I just want you to appreciate that there is some really interesting deep connection between circles on a sphere and circles in the plane given by stereographic projection, and that this correspondence allows us to think about inversion in the plane in another way, using sort of our three-dimensional space and points external to the sphere, sort of reflecting points in the sphere with respect to some external point. So it's a rich kind of theory, which is quite different from Euclidean geometry, but it's a rich, consistent geometry all on its own. The next important topic that I want to talk a little bit about is the re-emergence of projective geometry in the 19th century. So projective geometry in modern times has its origin with the work of Desargues, which I've already told you about, and Pascal also made an important contribution. But the subject was more or less forgotten about for a couple of hundred years. And then in the 19th century, a number of people started thinking about this again, and they had a crucial insight into the nature, the essential nature of projective geometry. And this also, Mobius was involved with this, also Plücker, and in fact there were a whole bunch of 19th century mathematicians very interested in projective geometry. So I want to explain that a little bit because it's also quite interesting in that a notion of infinity arises here, which is quite interesting. So a kind of a geometrical infinity, not a numerical infinity exactly, but a geometrical one. So here is an ordinary line with some usual kind of affine coordinates, okay? And the idea here is that we're going to look at this one-dimensional object from a two-dimensional point of view, okay? So this turns out to allow us a bigger picture. And the way we're going to set this up is we're going to think about embedding this picture in a two-dimensional plane whose origin is right here. Okay, so I'm going to make, so this is like the real x-axis, and this is the real y-axis, okay? And here is the origin of this two-dimensional plane. And now I want you to observe that points on this line here are in correspondence with lines through the origin. Okay, so there's a point on our original number line. And to this point, I can associate the line through the origin and that point. Okay, so every point on this line gives us a unique line through the origin. Okay, so choose one over here. There's another point that will have this line associated to it. So different points get associated to different lines. So do we get every line through the origin this way? What happens, for example, if we start going in this direction and we start looking at the lines through the origin that are determined by some variable point moving in this direction? Well, the corresponding lines are going to become sort of more flatter and flatter as we go further and further out. And after we're 1,000,000 miles out, the line joining, the point there will be, to us, indistinguishable almost from this horizontal line with the x-axis. However, we don't actually ever get exactly to the x-axis line because this line is parallel to that one, so they don't actually meet. But any little adjustment to it, and we do get a line which meets the given line. That means that this x-axis itself is somehow a distinguished line in this picture. Okay, that line there, okay, has a sort of a different role. And we might end up calling it like infinity. So the projective geometers realized that you could make a model, okay, a model of projective geometry by looking at lines in a space of one higher dimension. So the projective line can be realized as essentially one-dimensional subspaces or lines through the origin in this two-dimensional space. And when we do that, then the point at infinity ends up becoming completely unmysterious. Previously it had been mysterious. What do we mean by points at infinity? From this point of view, the point at infinity in the projective line is just that particular line through the origin, which happens to be horizontal. And there's nothing magical about it at all. And moreover, this gives us a way of describing things. So this line here, okay, is determined by that point. And that point has coordinates what? Well, maybe this point has coordinates, maybe that's a little bit more than a half. Maybe it's a little bit more than half. Maybe 11/5. That's a little bit more than a half, right? It's a little bit more than 1.5. Oh, sorry, 1.5. Okay. Maybe 11/7. How's that? That's a bit more than 1.5. Okay. So maybe that's the coordinates. 11/7, and the y coordinate will be 0. Will be 1. The y coordinate will be 1. Now, so this line here is determined by this point that lies on it, but in fact it's really determined up to scale by the proportion between these two things. So what we can end up doing, and this is what the 19th century geometers did, is they said, okay, what's really involved in describing this line is the proportion 11/7 to 1. It's the proportion. And a pleasant thing about proportions is that they're unchanged if you scale the two entries by the same factor. So in particular, we could clear denominators and say, well, this is the same as the proportion 11/7. Moving us from fractional arithmetic to integer arithmetic. So instead of fractional arithmetic with single numbers, we have sort of an integer arithmetic of these proportions involving a pair of numbers. And the beautiful thing about this is that this new line here, this horizontal line, which corresponds to some point at infinity, which is hard to express in the original system, can be expressed in this homogeneous coordinates system by looking at the point on here, okay, is going to be, so that point there is the point 1, 0, okay? And so this line is represented by the proportion 1/0. And that then, so that's really like infinity in this projective geometry. So this is a way of completely demystifying infinity in this geometrical sense. Instead of replacing it with something that's arbitrarily big or something like that, we just replace it with this really simple proportion, the proportion 1/0, which arguably is just as simple, maybe simpler than this one. So any proportion between two non-zero things, as long as they're both non-zero, represents a line, and that's called homogeneous coordinates. So this was a great advance because it allowed geometers to start understanding projective geometry arithmetically, indeed algebraically. And this became such a powerful tool that the 19th century geometers were able to start incorporating more and more of classical geometry into this somewhat bigger framework where you allow yourself points at infinity. This is just the one-dimensional situation. It gets more interesting when you go to higher dimensions. In 2 dimensions, you have to sort of add a whole circle of points at infinity, but it's all the same. It's just done with these homogeneous coordinates very simply. And so algebraically becomes actually quite easy to manage and enlarges the subject dramatically because it turns out that these points at infinity actually seem to have often important geometrical significance. Okay, so this subject with this new point of view, okay, initiated by Mobius also and Plücker and others, this new point of view was so powerful that in the middle of the century, Arthur Cayley, famous British mathematician, claimed that all geometry is really descriptive or projective geometry. That's sort of another name for it. That's probably a bit of an overstatement, but there was definitely this view that, okay, this is like the biggest geometry, that this geometry includes all others. It's a very interesting, powerful point of view. The next very important chapter in the story of 19th century geometry is the emergence of non-Euclidean geometry. And this is a very rich story. I do suggest that you have a look at my History of Maths lecture. I have an entire 1-hour lecture on this where I go into a lot more detail, and I think that's a pretty decent lecture. So I'm just giving you a bird's eye view, but you have to appreciate that this was really a monumental advance, and it really shook the foundation of mathematicians' thinking with regard to geometry. Suddenly there loomed in front of them or off to the side this alternate universe, which was somehow parallel to the one they were familiar with from Euclid. Okay, everybody was firmly entrenched in the logical structure and development of Euclid. But now suddenly there was this new kind of geometry, which on the face of it was very unfamiliar, but still obviously very rich. So it was kind of an alternative to the standard geometry. Now there was the question, okay, well, we have these different geometries around. Which is the actual true one? Does that question even make sense? So the story here is always associated with Lobachevsky, Bolyai, and Gauss, three mathematicians, Russian, Hungarian, Gauss, German, of course. And Lobachevsky actually published this first, and Bolyai independently. And then after the fact, Gauss pointed out that he had made a lot of investigations on this much earlier, okay, but had left off publishing it because he didn't want to shock people too much. So very roughly, okay, like in a couple of minutes, here is Euclidean geometry. And in Euclid's development, there are these 5 postulates, sometimes called axioms. These are sort of things that Euclid starts his work with, things that we're going to assume because they're kind of obvious, okay? And 4 out of the 5 really are kind of obvious, sort of, at least if you're drawing pictures. But the 5th one is more challenging. The 5th one says that if you have a line and you have a point which is not on the line, then there is exactly one. There's one and only one line through that point which is parallel to the given line. And what does that mean? It means that it doesn't meet it. No matter how far you go, these lines never meet. So there's exactly one such parallel line through a point outside a given line. So for a long time this was more complicated than the other postulates, and mathematicians tried to prove it independently. And eventually these 3 gentlemen started to realize that this did not follow logically from the others. In fact, you could create an alternate geometry in which it was not true. And that's hyperbolic geometry. It's sort of the starting point that they had. That you can imagine a geometry in which there's, here's a line, here's a point on the line, where there's 2 different lines, maybe even more, but at least 2 different lines which are passing through this point, which are parallel to this line in the sense that they don't meet that line even if you extend the lines. So this is really non-intuitive. But from my point of view, okay, this whole story is in some sense a manifestation of the over-reliance on Euclid. People were just too fixated on Euclid that they couldn't see the forest for the trees. In fact, okay, the reality is that non-Euclidean geometry had been well studied for centuries, if not millennia, before this. Okay? And that was in the context of spherical geometry, in the context of astronomy and the heavens, and in particular the Islamic mathematicians' work on the geometry of the sphere. Also, Indian mathematicians made contributions there too. And in fact, so did the ancient Greeks. Okay? So the geometry of the sphere also is a non-Euclidean geometry. But here you have to think of the lines as being these great circles that I was telling you about, the things that you get when you slice a sphere with a plane through the center. Now if you have some point which is on the sphere, not on this plane, there are 0 lines that pass through this point and are parallel to this given line. You take any plane, any great circle, which passes through the center and this point here. So there's a whole family of them. But any one of them will give you a line, in other words, a great circle, which will necessarily meet the equator that you're talking about. So this is a non-Euclidean geometry, but for sort of a different reason than this one is. Here we have more than one line which is parallel. Here we have no lines which are parallel. But nevertheless, this is a really valid, it ought to be just as valid non-Euclidean geometry as this one. In fact, ultimately, it was seen that these two geometries are sort of on different sides of Euclidean geometry, sort of somehow fits in between them. So from my point of view, there was a lot of confusion in the 19th century. So if they could listen to this lecture, 200 years ago, it would have been hugely influential because they just didn't think about things in the right way. They couldn't see that this spherical or elliptic geometry that was really completely in front of their eyes was actually a valid example of non-Euclidean geometry. And it turned out that, in fact, these two geometries, the theorems in them are very parallel. But that required the emergence of another figure, another key figure in the story. So this was Eugenio Beltrami, an Italian mathematician who quite some time after Lobachevsky and Bolyai, they did their work roughly in the 1830s. So he came up with these models of hyperbolic geometry, maybe 1870s, 1880s. And he was really the first person to logically put this geometry on the map in the sense of providing actually a completely clear model for what these geometries were really about. So in short, somewhat simplified, here is what he realized, that you could think about both the elliptic geometry, or spherical, almost the same thing, and the hyperbolic geometry in very parallel ways by going to 3 dimensions. So we're talking about 2-dimensional geometry, but we're thinking about it being embedded in 3 dimensions. We've already seen this as a key sort of idea to try to understand things in certain dimensions by looking at them from a larger point of view. We saw that already with inversive geometry. Something similar here. So the elliptic geometry, which is the geometry of the surface of a sphere, is naturally studied by thinking of the sphere as embedded in 3-dimensional linear space, given by an equation, x squared plus y squared plus z squared equals 1. That's the equation of a sphere in 3 dimensions. Okay, and he realized that correspondingly the hyperbolic geometry can also be viewed in a very parallel way just by making a single change of sign, by replacing this plus sign with a minus sign. And looking at what we call the quadratic form, x squared plus y squared minus z squared. It's a little bit more complicated. When you set this equal to 0, over here you just get the origin. But over here you get a cone, more complicated. And when you set this equal to 1, you get what's called a hyperboloid of revolution, a surface which has one branch which is like a hyperbola sort of rotated around, and here's the second branch on the other side, rotated around. And he realized that what Lobachevsky, Bolyai, and Gauss were really doing could be described as geometry on the surface of one of these branches of this hyperboloid. And what you do is you do really the same thing as you do over here for the sphere. To get lines, straight lines, what you do is you choose some plane that passes through the origin, and then you intersect, so it passes through the origin, and then you intersect the sphere with that plane, and you get a great circle. Let me draw it like this. Okay? So that's an example of like a straight line in the spherical or elliptic geometry. And over here, you do very much the same thing. You take a plane that passes through the origin, okay, and you intersect it with this hyperboloid, okay, and you're getting, okay, this thing carries on, so it goes up like this. You get essentially what looks to us as a hyperbola. And when you set this thing up in this way, then the parallels between elliptic geometry and hyperbolic geometry completely demystifies the subject to a certain extent. Okay, and a lot of things become much clearer. Unfortunately, this is not even taught in undergraduate courses very much. It's very unfortunate. And in fact, the whole story is sort of extended massively by what I call universal hyperbolic geometry, which is my own take on things, which says that actually what you really should be doing here, okay, is looking at this whole thing, but not just the portion inside this cone, but also the portion outside the cone, which maybe I can try to draw it here. The portion outside the cone is also a hyperboloid of revolution, but it looks something like this. So here's a typical sort of orbit. When you place the 1, say with a -1, you get a surface that looks like this, which is found in architecture quite a lot. Okay, and in fact, so when you're studying universal hyperbolic geometry, you learn that the same formulas, once you set them right in sort of the rational trigonometry format, work both for the geometry of this 2-sheeted hyperbola as well as the geometry of the 1-sheeted hyperbola. And there's a unification that goes on, okay, that you don't really just want to be studying one part of it. So Beltrami's understanding is a key point in helping us move to this much larger, more beautiful and more general point of view, which is universal hyperbolic geometry. Okay. But as you can see that we're expanding our vistas considerably here. I just want you to get an overview of this, this sense that from a sociological point of view, the 19th century people were carrying this big burden of Euclid on their back, and that somehow constrained their thinking to go in certain directions and not in others. So there's definitely a very interesting sociological aspect of this. So I'm just part of the way through the 19th century story here. But I'm going to finish the lecture with this other geometry. Another development is really important, which is the introduction of complex numbers into geometry, which transformed a lot of the subjects. So complex geometry, we can think of this as sort of getting 2-dimensional arithmetic for the price of 1 dimensions. Okay, so it's a really interesting thing that we're enlarging the arithmetic, okay? We're enlarging the arithmetic, and that ends up enlarging the geometry that's built up from that arithmetic, from a Cartesian point of view. So we're following Descartes and Fermat from looking at things in a Cartesian point of view in terms of coordinates. And then we realize, okay, so if we extend our number system from ordinary numbers to so-called complex numbers, then we can extend a lot of geometrical objects which are constructed from these coordinates also. So here is the usual number line, and it's best that you think about the rational number line. So 0, 1, 2, and then you can also subdivide. So there's 17 over 11, there's -7/3, there's 1/2. So rational number is more or less represented here, okay? And over here is the decimal number line, which is a number system used by engineers and physicists and sort of ordinary people, which involves subdividing by 10. So there's 0, there's 1, then we subdivide units of 10, and then we make further subdivisions, subdivide each one of these into 10 and so on. So we end up expressing numbers by decimals, and the more decimals there are, sort of the more accuracy we're talking about. But there's an approximate aspect of this. So a scientist thinks of 0.4 as not being an exact point, but actually sort of a range of values. Okay, something is measured and it's 0.4. It means that there's some indeterminacy. It means that the next decimal point is not entirely clear. There's some variability there. While this number here is representing a greater degree of accuracy. Okay? But the engineer never has complete accuracy, so infinite decimal is not part of this story. So I want you to appreciate this. Of course, the real number system is some kind of attempt to take this thing and sort of drag it into the exact world, so to pretend that we have an arithmetic of infinite decimals that extends this one, but sort of has the exactness of the arithmetic involved here. And as I've pointed out many times, that's very, very much wishful thinking. Okay, so what's the complex number story? So the complex number story is the realization that these pictures can be extended from their one-dimensional aspects to a two-dimensional aspect by introducing a new number called I, whose square is -1. And here's the usual story. So now there's the usual number line, much like this one in terms of fractions. And now here's a new axis, which notably has I on it instead of 1. And that allows us then to describe points in this plane in terms of an ordinary component, a fraction in the x direction, or the horizontal direction, and a multiple of I, in this case 1/2 I, in the I direction. Okay? So that's what a complex number is, and often denoted by Z. Okay? So that's a complex number, 4/3 plus 1/2 I. And to do arithmetic with these things, well, basically you use this crucial fact. When you add them, and you sort of add them in the obvious way, but when you multiply them, you have to use the fact that I squared is always equal to -1. Now that's just sort of an exact system, so I might call this the complex rational numbers. But there's also a kind of sort of engineering or scientific version where we work with approximate decimal quantities. So there's this point here, which is no longer quite as precise as over here, -0.9 plus 0.4 I, representing some kind of rough position. We could call these the complex decimal numbers. Okay. So it turns out, somewhat miraculously, that the arithmetic of these complex numbers is really, first of all, very interesting mathematically, but also ends up having huge implications for 20th century physics. So when people start doing quantum mechanics in the 1920s, they start to realize that the essential aspect of the workings of quantum mechanics somehow almost requires us to frame things in terms of complex numbers. This is a deep mystery that I think we still don't really understand. Why is this? Okay, it's pretty interesting. But it's telling us that these complex numbers are not just a figment of the mathematician's imagination. They do somehow connect very directly with the real world, or as much of that as represented by quantum mechanics. It has a little bit of an unreal aspect sometimes. All right, so now that we have the possibility of this two-dimensional arithmetic with complex numbers, we can look at complex geometries, which are roughly obtained by complexifying ordinary rational geometries. So what we do is we take some classical geometry, like the kinds I've been telling you about, and we think about replacing the underlying numbers which are involved with complex numbers. It's called complexification. And we get a rich theory, which is unfortunately much harder to visualize. So we lose contact a little bit with direct physical visualization. So it is challenging. And it's sort of beyond our ordinary experience in lots of ways. So this is challenging even for undergraduates. And a lot of undergraduates will only sort of dimly be aware of some of these things. So these are quite advanced ideas in some sense. But I just want to give you a flavor of it. Okay? So let's look at an example of complexification. So by taking a very simple kind of geometrical object, the circle. Okay, the unit circle with the equation x squared plus y squared equals 1 in the usual xy plane. There it is there. And here is a point on that circle. 4/5, 3/5. If you square this, and you add them, you're going to get 1. That means this point actually is on the circle. And it's 4/5 along here and 3/5 along here. Right? So we can represent this point really by 2 points on the axis. That point on the axis, which is 4/5, and this point on this axis, which is 3/5. Now, more generally, if you wanted to describe more general points on the circle, here is a really nice way of doing it. So this is algebraic parameterization of the unit circle. So we have these two expressions involving some parameter t, and if you plug in any value of t in here, then you're going to get a point on the circle. And all points on the circle are of this form, except for this one here. You might, as an exercise, try to figure out what the t value is that gives you this point. As a clue, I'll tell you what it is geometrically. If you join this point to here and look at that point there, its coordinate is t. Okay? You might like to see if you can figure out what t is. Okay, so now let's think about the question, how could we complexify this story? So it turns out that there's a number of different ways potentially of doing this, but the simplest is probably this. We just take this equation x squared plus y squared equals 1, involving sort of ordinary numbers. Ordinary for us means rational numbers, that's sort of the simplest kind. And we replace the rational numbers with complex rational numbers. So instead of x and y, let's use z and w. So we get z squared plus w squared equals 1. But now z is a complex number. And there's a copy of the complex plane. It's really the complex line, but to us it looks like a plane. This is a direct analog in the complex world of this x-axis over here. And here is the w plane, which is a direct analog of this y-axis. Now, you might say, well, why don't you make it sort of perpendicular? Yeah, I could try to do that, but then it becomes harder in some sense to visualize because it's hard for us to try to understand 4 dimensions. Okay, we can't, 2 dimensions this way, 2 dimensions this way, what does that look like? So I'm going to keep them separate. It's a little bit clearer. And I'm going to ask, okay, so what does this equation represent in this complex world? It's a pretty interesting question. If you're an undergraduate, you might like to think about this. So as an example, let's see if we can find one point on this sort of complex circle. So how are we going to do that? Well, so we want some analog of 4/5, 3/5. So what we could do is we could say, well, why don't we just use this same formula? This formula gives us points on this circle. But we have to put in rational numbers t over here. Okay, why don't we use the same formula and just plug in complex number for t, and hopefully we'll get z's and w's. So I'm going to illustrate some complex number arithmetic for you. You can check this if you have some familiarity with it. If you don't worry. It's just relatively simple, sort of high school kind of fiddling around with some complex numbers. Basically always using I squared equals -1. Okay, so what I'm proposing to do is to take this formula, call it E of t, and to plug in 1 plus I. Okay, so I'm going to get 2 numbers which are going to be complex numbers. Okay, so what do I have to do? Well, I have to take 1 minus 1 plus I squared over 1 plus 1 plus I squared. And over here, 2 times 1 plus I over 1 plus 1 plus I squared. Now, when you square something like this, like you square 1 plus I, you get the square of the first term, which is 1, plus the square of the second term. Square of I is -1. So you get 1 plus -1, plus twice the product. And twice the product is 2I. So now the 1 and the -1 cancel. So all you get when you square this is 2I. So this becomes, the numerator becomes 1 minus 2I. And the denominator becomes 1 plus 2I. Over here we have 2 times 1 plus I. That hasn't changed in the numerator. And this is again 1 plus 2I. Okay, so how do we simplify that? So in complex number world, what you do is you say, it's a quotient, one complex number divided by the other. So we have to multiply top and bottom by the complex conjugate of the bottom, the denominator. So the complex conjugate of 1 plus 2I is 1 minus 2I. When you multiply 1 plus 2I by 1 minus 2I, you get the sum of the squares, 1 plus 4, which is 5. And when you multiply this by 1 minus 2I, well, it's like squaring this. You're going to get the square of the first term, which is 1, the square of the second term, which is 4I squared, or minus 4, plus twice the product, which is minus 4I. So altogether, you can get minus 3/5 minus 4/5 I. And you do the same kind of thing over here. You get 6/5 minus 2/5 I. So we're getting 2 complex numbers. Let's picture them. Okay, so here's this first one is z. So it's sitting somewhere in the z plane. Okay, there's 1 minus 1 I minus I. So where's minus 3/5? Okay, you have to kind of go minus 3/5 over there, and minus 4/5 I, minus 4/5 down here somewhere, right? So it will be, there. Okay, that point represents that number. And what about this one? Well, this is in the w plane. So we have to draw it up here somewhere. The first coordinate is 6/5, so that's about over there somewhere. Minus 2/5 around there. So the number is there. So these two things here that I've drawn sort of correspond to these two things in the corresponding axes. Okay. So the point that we're getting in this complex circle is the point which is, well, this is it. This is the point. And we can visualize it as a pair of complex numbers. The pair consisting of that point and that point. So that's one point on this complex circle. Okay, what does the rest of it look like? Well, that's an interesting question. And if you have some mathematical experience and you don't already know, you might like to play around with this and try to get a sense of what this circle looks like. But one thing that's certainly going to be clear is that this is going to be essentially, from our point of view, a two-dimensional object. The circle is one-dimensional. That's true. But here we're talking about something which is given by a one-dimensional parameter, but the parameter is allowed to range over the complex numbers, which for us is a two-dimensional kind of range. So when we look at this somehow, we're seeing some kind of surface in this four-dimensional space. And that sounds complicated, but it's also interesting because technically it should be like a circle. So we might ask, like, of all those hundreds of theorems of circle geometry that are known, do any of them apply to such a circle? What happens? And once you start thinking in this way, then all kinds of new things open up, because you can take all these classical curves that people have been studying for hundreds of years, and you can start looking at them from a complex point of view. So in the 19th century, we had these sort of two great, well, a number of great enlargements, but in particular, in terms of the study of curves, we had this point of view of looking at the projective aspects, including points at infinity. And we had this idea of extending our number system to complex numbers. So those two things are really created all kinds of new developments in geometry, projective geometry / algebraic geometry. Okay, so I've covered a huge amount of territory here. I hope you don't worry if you haven't understood it all. I want you to get a sense of it. Okay, and there's more to come in our next video because we're not finished with the 19th century. I'm Nolan Wildberger. Thanks for listening.